Right folks, question 1a, keyword here is intermolecular, between molecules, and you need to identify two substances that have them between their particles. So associate the word intermolecular with covalent compounds. There are 3 covalent compounds in this and substances in this list, and then think which of these have molecules that can attract each other, and choose 2. Okay, in part B, you've got 6-mark question here, which is comparing. There's the command word, compare the structure and bonding of the 3 compounds. So you've got information, carbon dioxide, magnesium oxide, silicon dioxide. So when you're planning your answer here, think, what are these substances made out of? Are they made out of atoms or ions? Think, is the structure giant or simple? Can we say anything about intermolecular forces? And then can you compare their bonding? What type of bond? Is it strong? What are the bonds made out of? And then within the substances themselves, you could think about comparing how many bonds there are. Right? This question is not about properties. You are not writing about melting point. You are not writing about electrical conductivity. Purely about bonding and structure. Okay, question 2. You've got some information about melting point. Students often mess up here. Remember that if a substance is colder than its melting point, then it will be solid. If it's above its melting point, but below its boiling point, it's a liquid. And if it's above its boiling point, it's a gas. Okay, part B is asking you to explain trends, in this case in boiling point. So within a group, remember the trend is always related to how large the atoms are. And remember that the halogens make molecules of 2 atoms. So fluorine exists as F2, and going down the group you'd have Cl2, Br2, I2. And remember, going down a group means that your atoms are increasing in size each time. And if we're writing about boiling points, we're thinking about how much energy do I need to make the particles separate from each other. Part C is a little point here for you to note that the properties of a substance, when you have a normal amount of it, so if we had several litres of bromine, the properties of the bromine are not the same as the properties of individual atoms. Okay, one way of describing that is to talk about bulk properties. Okay, so this question is saying, why is the boiling point of a single bromine molecule it's not correct to give it a value. Okay, think what to boil means. It means to separate molecules from each other. Okay, part D, we're being asked why we should do it in a fume cupboard. Something must be dangerous. Something in this experiment you wouldn't want to breathe in or have floating about in the room. What is it? And say why it's in a fume cupboard. And part E, 3 marks to talk about trends in reactivity. Remember, the trend in reactivity is related to the ease with which the atoms form ions. So you need to be talking about how the size of the halogen atoms relates to how easily they gain electrons, because remember group 7 all want to gain 1 electron. Okay, some guidance here for question 3a. We've practiced this. Magnesium chloride, an ionic compound made of magnesium ions. Note that they are 2+, and chloride ions, which are 1-. make 4 clear points describing what the magnesium atoms do with their electrons to become ions, what the chlorine atoms do to become ions, and then what happens when the oppositely charged ions attract each other, and think about what the formula of the magnesium chloride will be. How many of each type of ion will be in magnesium chloride? Okay, throwing in some question about electrolysis, which relates to the properties of ionic compounds. Remember, the whole point of electrolysis is to use electrons to separate a compound, to split it up. We're remembering that when ionic compounds are melted or dissolved, the strong electrostatic forces are overcome and the ions are free to swap positions and move around. A lot of electrolysis, looking at part B, part 2, can be explained by the fact that opposites attract. And for part 3, remember that when you have a solution, you haven't just got the magnesium and the chloride ions, you've also got water, which we think of separating into hydrogen and hydroxide ions. So the gas at the negative electrode will be a positive ion. Think about which one that will be. Remember your rules for electrolysis. You only get the least reactive ion being produced at the negative electrode, and that choice comes down to, is it the metal in your ionic compound, or is it the hydrogen from the water? Have a go at balancing part 5. Remember, these half equations show what happens in terms of electron loss or gain. And finally, part C, this question is about metallic bonding and the arrangement of the metal ions in a piece of solid magnesium. You're explaining why the atoms can move around each other and therefore metals are malleable. They can be bent into different shapes. Okay, we've done some revision on chemical analysis, flame tests, and tests for different ions. You've just got to learn these, find the correct answers to these, look them up if you have to. Okay, question 5a, you've got some information about sulfur hexafluoride. It doesn't matter that you've never heard of it, perhaps. It tells you it's insoluble, it tells you it's extremely unreactive, and it tells you it's used as an insulator. Note that this is 2 non-metals, and you know which type of bond forms when 2 non-metals are sharing electrons with each other. Part B, anything about boiling point, we're writing about the forces or the bonds between molecules. Better to avoid the word bond and talk about intermolecular forces. 3 properties. You're going to pick out the properties from the information above. So if you look at the information, you will be able to highlight things that are true about sulfur hexafluoride that will make it useful as an insulator. Okay, question 6. You've been given a choice of compounds here: carbon dioxide, ammonia, methane, water vapor. All of those compounds are simple molecules. And you know the type of bonding between non-metals. You are writing here about covalent bonding. Try to make 4 clear points about what is happening. Okay? Note that it says you must include electronic structures in your explanation. You need to tell the examiner, show the examiner that you understand what is happening with the outermost electrons in these atoms. Alright, finally, we've got a fact that glass is made from silicon dioxide at the start of question 7. A fact that silicon dioxide has a very high melting point that we should already be happy with. It's a giant covalent structure, lots and lots of very strong bonds holding the silicon and the oxygen together. The question is asking you why glass has a lower temperature melting point than the silicon dioxide, and so it must be something to do with the bonds in the glass compared to the bonds in the silicon dioxide. Make a suggestion. What is it about the bonding in glass holding the atoms together that is different to silicon dioxide that makes its melting point lower? Part B is asking you to write a formula. Remember the rule about writing formula. The total charge of positive and negative has to cancel each other out. So whatever you write down, the number of sodium ions and oxide ions will produce an overall charge of 0. The total pluses and total minuses will be equal. And part 2 is a question about covalent bonding. You're being asked to show what happens when one oxygen atom shares electrons with another oxygen atom to make an oxygen molecule. Remember, oxygen is in group 6. It needs 2 electrons to complete its shell. It's going to make 2 covalent bonds with itself. Finally, for part C, you're describing the metallic bond. Think how you're going to describe it. Imagine the picture in your head. All right, and to get good marks, really good marks here, don't think of metals as being made of individual atoms. Think of them as being made of ions, because we know that their outermost electrons are free to move around, and you need to reference that in your explanation of what the structure of a metal looks like.